In the last lecture, we considered circular motion. We found that when an object moves in a circle, it experiences a force which acts towards the center of that circle. That force is called centripetal force. We now take up problems associated with the circular motion. Many of these are very important and also very interesting phenomena, and therefore, we will now start with these problems. A child of mass 25 kilogram is sitting on a horizontal merry-go-round making 6 rounds in 1 minute. If the radius of the merry-go-round is 5 meters, what is the centripetal force experienced by the child? This is straightforward. If you remember the formula 4 pi squared m nu squared r, then you can just plug the numbers and get the force. If you remember the formula, you will get just plug the numbers and you will get the force. If you do not remember, then you can find the velocity in fact, and then mv squared by r you can compute. It makes 6 rounds. So, it covers a distance of 6 times 2 pi r in 1 minute. So, we can find the velocity is 6 into 2 pi r divided by 60, which is pi meter per second. And now, the force is mv squared by r, m mass is 25 kilograms. So, 25 pi squared by 5, this is again 5 pi squared n, which is 49.35 n. So, whichever way you want, you can do it. This is a very simple example just to illustrate how the centripetal force is calculated. Let us take another example. This is about the banking of roads. A car is moving on a circular track of radius 300 meters banked at an angle of 15 degrees. Is it safe to drive on this road at a speed of 30 meters per second? That is the question. Let us find out the safe speed. So, I am just to recapture, I am writing these equations. N sin theta is mv squared by r. You remember from the last lecture, n cos theta is mg, and we have made the various components shown here. If you can sketch the problem, it helps a great deal. That is why I tried to sketch this problem. Recall that the safe speed on a banked road is given by the root of r g tan theta. So, we plug the numbers and we find that v is 28.35 meters per second. So, driving at 30 meters per second on this road is not safe. The same question could also be posed somewhat differently. At what speed should a car be driven on this track so that there is minimum wear and tear of the tires? We calculated this last time, that the speed should be v equal to r g tan theta square root of that, so that there is no wear and tear of the tires. So, we have calculated r g tan theta square root of that, and that is 28.3 meters per second. So, if on this road you drive at a speed of 28.3, you would increase the life of the tires of your car, and it will benefit you a lot. You will be safe as well as you will be saving money on your tires. Let us take another example. In question 2, we did not have any friction. Now, we add friction also to the problem. So, we are given that the coefficient of static friction between the track and the tires of the car is 0.2. Is it safe to drive on this track at a velocity of 30 meters per second? We have the same track, but now we take into account the friction provided by the tires and the road. So, we are given r equal to 300 meters, that is the radius of the track, theta is 15 degrees, that is the angle at which the road is banked, the coefficient of friction is 0.2, and we recall the formula V max, if you remember, is the square root of g r times mu s plus tan theta divided by 1 minus mu s tan theta. Plug the numbers and you get V maximum equal to 38.5 meters per second, which is larger than 30. Therefore, it is safe to drive at 30 meters per second. And you notice one thing, that the addition of friction has increased the safety on that road. So, friction adds to safety. That is why tire companies spend so much money on advertising how their tires increase friction. This is for just the sake of drawing a graph. I have plotted this function f as a function of the coefficient of friction, and you can see as the coefficient of friction increases, the safe speed increases. Same thing, as tan theta increases, the safe speed increases. Let us take another example. Now we bring another element, the tension in the string. A particle of mass m is whirled in a horizontal circle of radius r with velocity of magnitude v by a string suspended from a point as shown. What is the angle that the string makes with the vertical? I have drawn here the figure. This is the string, there is a tension T, this is the object of weight mg, and this tension can be broken up into two components, T cos theta vertical and T sin theta horizontal. And remember that the particle is moving like this, the object is moving like this, therefore, it experiences a force towards the center shown by red arrow. This force is the centripetal force. So, everything is here. So, in the vertical direction we have T cos theta equal to mg, in the horizontal direction we have T sin theta equal to mv squared by r, and from this we can find tan theta. Tan theta is v squared by rg. That is, the angle made by the string with the vertical is tan inverse of v squared by rg. Let us consider now the motion of an object in a vertical plane. What is the difference? The difference is that in a vertical plane we also have to take into account the force due to gravity. So, let us look at this object. This is moving in a vertical plane, and at the highest point in this circular orbit, the weight is acting downwards, the centripetal force is also acting downwards. And if we recall that the centrifugal force offsets the force of gravitation, then you can see that in this case the centripetal force supplies part of the weight of the object mg. So, the effective weight of the object would be W equal to mg minus mv squared by r, because part of the weight has been supplied by the centripetal force. If the velocity of the merry-go-round is such that mv squared by r is equal to mg, then the weight is 0. That is, at the top of this circular path, the object will have weight 0 if mv squared by r is equal to the weight of the object. In other words, the centripetal force will then completely support the weight of the object. What happens at the lowermost point? Now, the weight is still acting vertically downwards, but the centripetal force has changed direction. So, therefore, the equation of the apparent weight would now be mg plus mv squared by r rather than mg minus mv squared by r, which was at the highest point. At the lowest, it is mg plus mv squared by r, and if mv squared by r is equal to mg, so that at the top the object does not have any weight, at the bottom it has the weight equal to twice its own weight. Let us continue with this, very interesting also. A person is going over a hill with a velocity of 30 meters per second. If her mass is 60 kilograms, what is her apparent weight at the top of the hill? If she passes the lowest point with the same velocity, what would be her apparent weight there? The radius of curvature of the hill is 400 meters. So, I have sketched here for you the kind of thing that this person is doing. This is the hill, she is at the top of the hill. At the top of the hill, the surface of the hill provides the normal reaction, and that is n. The weight is acting vertically downwards, the centripetal force is also acting downwards. At the lowest point, the weight is still vertically downwards, the reaction is still vertically upwards, but the centripetal force now is acting upwards. In this case, it is downwards, here it is upwards. So, let us see what happens. So, we write down the equations for the balance or for the equilibrium. You see, n is the reaction, mg is the weight, and the difference is provided by the net force acting, or F net. And what is F net? F net is nothing but the centripetal force. At the top, it is mv top square by r, at the bottom it is mv bottom square by r. Now, there is a sign change here. Why? Because as I pointed out, the centripetal force has changed direction. Here it was downwards, here it is upwards. So, this has changed direction, and therefore, we have n minus m g equal to minus m v top square by r, and here n minus m g plus, you see we have adopted a certain convention in which we have taken n to be positive. If n is positive, then m g is negative and the top centripetal force is also negative. At the bottom, n remains positive, m g remains negative, but this has changed sign because this becomes now positive. So, we adopt a certain convention and we write these equations. The normal reaction is the apparent weight. You see what is weight? If I put something on it, then the weight is given by the normal reaction of the surface. So, the normal reaction is the apparent weight of the object. At the top, n is equal to m g minus m v top square by r, and the bottom n is m g plus m v squared by r. So, just substitute the values of the velocity at the top, velocity at the bottom, the weight of the person, the radius of the hill, and we get the apparent weight at the top is 60 into 9.8 minus 90 newtons, which is 498, and at the bottom it is 60 into 9.8 our own weight plus that due to centripetal force, which is 90 newtons, and it is therefore 678 newtons. So, the person feels lighter at the top of the hill and heavier at the bottom of the hill. You must have experienced this. If you sit in a merry-go-round which takes you in a vertical circle, at the top you find that your weight has decreased, and if it is very fast you will find weight less. At the bottom you feel that you have more weight than the actual weight. In the above example, if a body were moving inside a circular track, then the normal reaction will be downwards at the top and upwards at the bottom. You see, in the earlier example, let me recall, reaction is always perpendicular to the surface. In this case it was upwards, and in this case it is downwards, because there is a track and the object is moving on that track, and therefore track exerts the normal reaction force. So, here the normal reaction force is downwards, m g is also downwards, and m v squared by r at the top is also downwards. At the bottom, the m g remains downwards, m v squared r is now upwards, and the reaction is also upwards, because the reaction is, as I said, perpendicular to the surface. So, our equations are n plus m g equal to m v squared by r and n minus m g equal to m v squared by r. We have adopted again a certain convention in which m g is taken negative in the downward direction. So, n plus m g is m v squared by r and n minus m g is m v squared by r. It is all related to the directions. So, you can fix the direction of n or m g or m v squared by r and rewrite these equations, but this is what you would get. Since this is important, let us consider this once again to make things easier for you to understand. You see, here we have an object which is moving inside a circular track. When an object moves on a surface, it experiences the normal reaction. So, the normal reaction at the top is downwards, the weight is also downwards, and the centripetal force is also downwards. At the bottom, the weight remains downwards, but the normal reaction is now upwards and the centripetal force also is now upwards. So, if we adopt a certain convention about the directions of these forces, then we get these two equations. N plus m g is equal to m v squared by r and n minus m g is equal to m v squared by r, and given m, v, r, etc., we can calculate the velocity required or the normal reaction or whatever is required to be done. Now, we take the same thing, but this time the particle is being whirled in a vertical circle by a string. We have a string and we are whirling the object in a vertical circle. Therefore, in this case, instead of the normal reaction, we have the tension in the string, and the tension, you can see from this figure, the tension plays the same part as the normal reaction, and therefore, the equations now are also the same, except n has been replaced by t. So, we have at the top we have t plus m g equal to m v squared by r, at the bottom we have t minus m g equal to m v squared by r. Again you can adopt a certain convention, so that the forces along downwards are taken as positive or forces along upwards are taken as positive, and when you adopt that convention and follow that convention, you will find these equations, and from these equations you can find the tension in the string. Suppose the centripetal force or the velocity with which the object is moving is such that m v squared by r is equal to m g, then the tension is 0. That means, if the object is moving with a certain velocity, so that m v squared by r is equal to the weight of the object, then when it is vertically upwards at the top of the circle, then the string does not have any tension. Whereas, at the bottom, if m g is equal to m v squared by r, then the tension is twice the t, because m v squared by r is equal to m g, and therefore, t is equal to m g plus m v squared by r, and if the two are equal, then the tension is twice m g or twice m v squared by r. So, the tension increases as we move down and is maximum at the bottom. At the top, the tension is minimum, it can be 0 if m g is equal to m v squared by r. Why is it so? Because the centripetal force, as I have been saying again and again, centripetal force balances the or provides the weight of the object. So, therefore, the tension, since centripetal force provides the weight of the object, the string does not have to have any tension to pull the object back. Lastly, we take an example of a popular game which you might have seen in many fairs or amusement parks and so on. What is this game? A popular game at most fairs is a motorcyclist completing a vertical loop. What the motorcyclist does is this loop, and he does not fall, and we have to find the condition so that he does not fall. What is the minimum speed necessary for a rider to successfully go around a vertical loop of radius 10 meters? You see, if that velocity is not maintained, then the poor fellow would fall. So, person must also know the centripetal force and therefore, have enough speed so that he does not fall. We have derived the above equation n plus m g equal to m v squared by r, where n is the apparent weight, and if v is such that m v squared by r is equal to m g, then the apparent weight is 0. So, if the minimum velocity is such that m v squared by r is m g, then apparent weight of the object is 0, and therefore, it does not fall. You know what is weight? Weight is the attraction due to the earth, and if this weight is apparent weight is 0, that means there is no attraction of the earth at that point. That means the object would not fall. So, the cyclist must know the velocity with which he must perform this loop. At the bottom, of course, the apparent weight will become twice, but that is not important. For him, the important thing is that he does not fall. And when does it happen that he does not fall? That v is such that m v squared by r is equal to m g, and we can find out, given the parameters r and g, we can find out what this velocity should be. So, in this lecture, we have tried to highlight some of the problems associated with the circular motion and how to tackle them. In the next lecture, we shall consider collisions between objects of various sizes and masses. We shall see a few interesting applications of the knowledge that we gain of the collisions.